In this video, we will review parabolas, and I want to focus especially on where the equation of a parabola comes from. Okay, so here is the setup. So let's let P be a point in the xy plane. Okay, so if I draw a picture, of some axes, so I got my y-axis and my x-axis, so x and y. So somewhere in this plane, I'm going to draw this point P. Let's say I put it here. This point, I'm going to call it the focus. Okay, so P is called the focus. And now I'm going to draw a line in the xy plane. I'm going to let L be a line in the xy plane. And this line is going to be called the directrix. So the directrix. So I'm going to draw a line, and just for simplicity's sake, I'm going to make my line horizontal. So I'm going to make it parallel to the x-axis. So if my line looked different, if it wasn't parallel to the x-axis, the graph that I'll eventually end up drawing will look a little bit different. It'll be angled differently, but it'll have the same overall shape. Okay, so this is L, and that's my directrix. Directrix. And what I want to do now is I want to consider all points x, y, such that the distance from the point xy to P, to the focus, is the same as the distance from xy to L, to the directrix. So in other words, I want to consider all points that are the same distance from the focus as they are from the directrix. So I'm going to sketch some of those points. So one point that's the same distance from the focus as it is from the directrix is, if I were to sort of draw a perpendicular from the point P to that directrix, the midpoint of that line is the same distance from P as it is to the directrix. Okay, so let me erase that line that I had drawn. Okay, so that point is definitely the same distance between P and the directrix, but there are others. So if I draw something over here, let's say, and just if I connect that with P, with the focus, and then I connect it with the shortest possible path to the directrix, because that's how I get the distance to a line, shortest possible path, so perpendicular, it looks like those two line segments are about the same length. So let's draw another one of these. So let's say I had a point maybe here-ish. So maybe here-ish, this looks like it's the same distance from P as it is straight shortest path down to the directrix. And if I keep going like this, if I keep going and I connect these points, they form this sort of shape. And I could even go in the opposite direction. In the opposite direction, I would have a point like that. That's the same distance from P and the directrix. And I get a graph that sort of forms with this shape. And that graph, we might recognize, is a parabola. That graph is a parabola. Okay, and we can verify by setting up equations for the distance on the left to P and the distance on the right to L, to the directrix, that when we set up this equation and simplify it, we get a quadratic that will happen. And we know the equation of a quadratic like this yields a parabola. So I'm not going to go through those details, although I think that is an interesting exercise to do, because I want to spend more of our time on doing some examples to review parabolas and how we graph them. All right, so a cool fact about this, about parabolas, is if we have an object that comes towards the parabola perpendicularly to the directrix. So what I mean by that is, if I have an object like this that comes straight perpendicularly down towards the directrix, when it bounces off that parabola, it will ricochet and go straight to the focus, no matter where it came from. So if it came this way and then it ricocheted off, it would go to the focus But anywhere else in the parabola, even if it's a higher point like this, coming in over here, when it bounces off, it'll bounce off and it'll go to the focus. All right, so one of the things in the real world that sort of takes advantage of that property of parabolas are satellites. So one example of parabolas are satellite dishes. A satellite dish. Another really common one is just motion in free fall of objects. So objects that are launched freely in the air. So objects, so not things like rockets or whatever that have additional propulsion, but just if you throw an object in the air, its motion, its path that it takes in the air, is a parabolic path. All right, so let's do some examples. So let's graph the following parabolas on the same set of axes. So we have these 5 parabolas. I don't want to graph them on the same set of axes. I'll get us started. I'll draw some axes. So I'll draw a y-axis and an x-axis. And I want you to pause the video and try this for 2 minutes. This is a good review question. 4, 3, 2, 1, pause the video. Pause the video and try this for 2 minutes. All right, so hopefully you've done that. Hopefully pause the video for 2 minutes to try this, to try to graph these. So let's start with y equals x squared. So I know that's an upward facing parabola because the leading coefficient, the number in front of the x squared, is technically a 1 here. That's positive. So it's an upward facing parabola and the vertex is at the origin. So y equals x squared. This is probably the parabola that we've seen the most. That we would have seen the most in our math classes, y equals x squared. So when we put a 2 in front of it, like part B, what that'll do is it'll stretch it vertically by a factor of 2. So this stretches it vertically by a factor of 2. In other words, that means it takes all the y values and it'll double them. So if I take a point like this on the parabola, it'll double its y value and it'll be up here. Or if I take a point like this on the parabola and I double its y value, it'll be way up here. Or if I take the vertex and I double its y value, well, its y value is 0, so it doesn't go anywhere actually. And if I start to connect these and form this graph, I get another parabola. It's just narrower. It's taller and narrower. I get something like this. That is y equals 2x squared. All right, so for C, we have the 1/2 in front of the x squared. That means it's going to stretch vertically by a factor of 1/2. So the y values are going to get smaller. So for a point like this, its y value is going to get halved, so it'll be down here. From the next point that I had drawn before this point, its y value is going to get halved, so that's somewhere here. And if I start to connect these, I get a parabola that looks like this one looks wider. Wider and flatter. And that is the graph of y equals 1/2 x squared. So that's how having a different positive number in front of the x squared is going to affect the shape of our parabola. When we stick a negative in front of these, so from A to D, we put a negative in front of the equation. And same thing from B to E. We put a negative in front of the formula. What that does is it reflects our graph across the x-axis. This is some review again from algebra, doing transformations on graphs. And it does that, it's going to flip it across the x-axis since the negative that we're putting in front of our formula changes the y value of points. And it'll switch the sign. Okay, so let's draw the reflection of y equals x squared first. So I'm going to draw y equals negative x squared. So negative x squared, when I flip the graph of y equals x squared, it'll look something like this. Flipped it across the x-axis. So that is y equals negative x squared. And now let's flip y equals 2x squared across the x-axis. So when I flip that one down, it'll look narrow again. It's just going downwards now. And that's the graph of y equals negative 2x squared. All right, so that was hopefully a review example graphing these parabolas. So let's do another one. So let's graph the following parabolas on the same set of axes. So this time we just have 3. So let's begin by drawing some axes. I'll draw a y-axis and I'll draw an x-axis. So for A, we have x equals y squared. Well, that's a sideways parabola. So x equals y squared looks something like this. It's still got its vertex at the origin, but it's extending sideways. So that is x equals y squared. With the next equation, now when we put a 2 in front, so the 2 is going to multiply the y squared. And that'll give me what x equals, because x equals 2 times y squared. Okay, so this 2 is doubling what the x coordinate used to be. So it's going to stretch it. This one is actually stretching it horizontally by a factor of 2, because the roles of x and y have switched here. So if I look at a point on my parabola, the x coordinate is now going to double. So that would put the x coordinate here. And if I look at a point a little bit further, its x coordinate is going to double. So that would be maybe here. And if we start to connect these, we get a narrow sideways parabola. And that's the graph of x equals 2y squared. If we do the same thing for part C, putting this 1/2 in front means we're going to stretch it horizontally because it's x equals this thing by a factor of 1/2. And that's going to make our parabola wider. It's going to make it look something like that. Okay, so that one is x equals 1/2 y squared. In terms of our goals for this section, we've now talked about where the equation of a parabola comes from. So that was that picture with a focus and a directrix, and done some review examples on graphing parabolas. So in the next video, we will talk about ellipses and where they come from.